Hello everybody, this is Miss Martinez again. We are going to talk about interpreting quadratic graphs today. So what exactly, do these quadratic functions represent, and how can we describe them in terms of its context, so anything real world. We linked the PDF for these notes in the agenda if you have a printer and have access and can print them. But if you don't, then the key for this will be posted, and I recommend that you copy down as much as you can in your notebook, and then you can just use that key as a reference, okay? And that will work for any of these notes that we do during AMI days, okay? So we've got a graph here that is representing an object that is being projected upward from ground level. Right? Oh, let me change that. Okay, so from ground level, we're projecting up and then launching back down. Okay. Height is h and the time is t. Okay, so height is our y value, and time is our x value, basically. Okay, so we can label those. It's always important to be consistent with what variables you're using if you're talking about context. So they're using t for time here, and then they're using h for height. Okay, so let's talk about this graph, thinking about just some random object being projected. Okay, it could be anything you want. So the first question is, when is the object at ground level? So this is asking when. Okay, that's the key word. When is it at ground level? Okay, so ground level is going to be 0 feet, right? So another way of putting this in function notation, which we've seen before, is asking when is h of t equal to 0? So remember, when you're using function notation, that h of t, very similar to f of x, that is just like y. So all of our y values here are h of t values. So we want to know, when is that height equal to 0, basically? Okay, so that's down here. A height of 0 is here. And then we need to look, does this happen anywhere else? Remember the symmetrical shape of a quadratic function. If you kind of go along your x-axis here and look, it's also going to be at ground level when the object lands over here. Okay, and so notice that the y values, or the h of t values, on those coordinates are both 0. Okay, and so we're asking, when does this happen? So look at your x value, look at your time. And that happens at 0 seconds, and then again at 8 seconds. So restate the question. The object is at ground level. Before it is launched. At 0 seconds. Then again when it lands. At 8 seconds. Okay. Okay, next one. What is the maximum height of the object? Okay, so it's asking what is the maximum height of the object. So let's go up and find that maximum value. Up here, that's also our vertex. But remember, height is an h value. So we need to be looking at what that h value is. And so that coordinate is labeled as 416. But the 16 is the actual height there. So we could go and look at the y-axis, or we could just look at that y or h of t value of 16. So our object does not go any higher than 16 there. Another way of asking this in function notation, if you look at that coordinate, the x value that goes with it is 4. So in other words, it's also asking what is h of 4? So anytime you have that, the t has been replaced with 4. So it's asking when time is 4, what's the height there? So we know that that is 16. We can say the maximum height of the object is 16 feet. And of course, if we knew what the object was, we could be more specific. So the more specific, the better when you are interpreting. Okay, so now it's asking, when is the object at its highest? So if it's asking for when, am I asking for a t value or an h of t value? When is time. So same thing, look at that height of 16, and we already know that the t value that goes with that is 4. Right here, that is 4. Okay, so it's at its highest after 4 seconds. Okay. Also, the other way of asking this in function notation, it was asking for the t value. It was giving us the h of t value. So asking at what time t is h of t 16? So basically asking what is t when h of t is 16, or the height is 16. Okay, next one. What is the height of the object at 5 seconds? So our answer is going to be a height. What is the height at 5 seconds? Or in other words, what is h of 5? So 5 has been replaced there for t, and we want to know what that height is. So we can go on our x-axis to 5 seconds and find the height value that corresponds with it. So this is 5. And so the point that goes with that is up here. I'll label it. So that is 5. And then that height must be 15 since it's one below the 16. So that's 15. Okay, so we can say the height of the object at 5 seconds is 15 feet. Okay, next we have domain and range. So talking about these in terms of context. Now notice we only see quadrant 1 of this graph. We don't have any negative values, and that's usually because when we're talking about any function in context, typically we really only look at those positive numbers, because a lot of times, especially for time and height, negative values don't make sense. We don't have negative height unless we go underground, and we don't have negative time, really. So that's not really going to make any sense for us projecting some sort of object, you know, like launching a rocket or shooting a basketball or something like that. Okay, so let's start with domain. Remember, domain are your x values. Or in this case, it would be t. So our domain is t, our time. Okay, and if we look at this graph that's representing this object, we want to write an interval that shows the smallest time to the biggest time that this object is launched for. So we're looking at our x-axis here, from here to here. And that smallest time is 0 seconds. And then the biggest time where it lands is 8 seconds. And now these are included. These are part of the process. 0 seconds is when it launches. 8 seconds is when it lands. So these should be included in our interval with brackets, the hard bracket. So 0 to 8. And if you were asked to interpret this, this would be a time interval. So how long object is projected. Okay. So next, let's talk about range. So range are your y values or your h of t values in this case. So we're looking up and down here on this y-axis. And which of those values represent the heights that our object goes from, the very smallest to the very biggest. So the very smallest I see is 0. And then earlier we said the highest that it goes is to 16. And these are also included. The object will be at 0 feet when it launches and lands, and the object will reach 16 feet because that's its maximum height. So again, we will use the hard brackets for these. And so your range in context for this situation is going to be your height interval. Okay, and then lastly, we have interpret the vertex within the scenario. Okay, so the vertex is always really important whenever we're using quadratic models. And so you might be asked to interpret it, and you definitely want to be able to understand it when you're using quadratic models. So our vertex here, remember, is 416, and we've already kind of dissected the pieces of it. 4 is your time, so at 4 seconds, the object is at its maximum height of 16 feet. So that's all we're going to say. We're basically just going to combine those two things together. That your vertex is where something reaches its maximum or minimum value. So we can say, after 4 seconds, the object reaches its maximum height of 16 feet. Okay, because the vertex was 416. Okay, hopefully that helps. Let us know if you have any questions. The key for this will be posted in Echo.